All right, how many of you already been through the thermo stuff in chemistry? AP Chem. So most of you. So hopefully this stuff won't be new for most of you. Start off by making sure we know the difference between heat and thermal energy and temperature. Those are three words that sound a lot alike, but in physics they have different meanings. Heat is thermal energy that's moving. And heat always moves from a hotter place to a colder place. Thermal energy works sort of like, temperature difference works sort of like what we're talking about in class right now. Pressure difference. Pressure always moves things from high to low. Pressure difference does. Temperature difference always moves heat from highest to cold, higher to lower. Thermal energy is the internal energy of something's atoms and molecules, the way they're moving. So it's measuring how fast the molecules inside something are moving, essentially. But if we're talking about thermal energy, it's not leaving that thing and going to something else. It's staying in that thing, and we're measuring how much energy is in there. Heat is thermal energy that's moving from one thing or one place to another thing or place. And then temperature is just a way to measure the thermal energy, essentially. It's a measurement of the average internal kinetic energy, or we might think of it as the internal thermal energy of an object. You want to think of a thermometer sort of like a radar gun for molecules. That's basically what it is. It's measuring the speed of the molecules, the average kinetic energy. Most of the time in here, we're going to use which temperature scale? Celsius sometimes, but in this unit, we're going to deal with gas laws. And when you're dealing with gas laws, you got to use what? You got to use Kelvin. So we'll do a quick review of some of the gas laws a little bit later. Probably won't get there today. But we'll go through Boyle's and Charles and Gay-Lussac's and PV equals nRT and all those fun things. All right, now, I know that Ms. D, who's in AP Chem right now? Y'all just finished doing a calorimetry lab, right? So, you guys should know this. What is a calorimeter for one of you guys that's not them? What's a calorimeter?
Measures calories.
Yeah, let's say that you had a candy bar. And you wanted to know how many calories are in that candy bar. How do they figure that out? They take it inside a container, and usually they dry it out first so it's dehydrated completely. You put it inside a container, a metal container usually, and then that metal container gets put into what? Water. They measure the temperature of the water before they set the candy bar on fire. They set the candy bar on fire, let it burn all the way out, and then measure the temperature of the water after. And by knowing how much water you started with, and the temperature change in the water, you can calculate what? The energy. Because when you're dealing with a calorimeter, what are you assuming about energy lost inside the calorimeter and energy gained by the water? You're assuming they're the same. Now, is that completely ever going to be perfectly true? No, because some of that heat's going to be lost to the container itself. Some's probably going to get out the top. But most of the energy that's lost by that thing burning inside is gained by the water. When the water gains energy, what happens to it? The temperature goes up. Or, if it gets hot enough, what happens? It may boil, it may change states, and we'll get to that in a minute. But right now we're just going to deal with it when its temperature changes. And what we're going to talk about first is this definition. This definition is not for calorimetry. Wait, what's that the definition for? I guess it sort of is. But what we're dealing with on this slide is basically what's called the specific heat of something. Yeah, the specific heat is how much energy it takes to raise what? Yeah, 1 unit of that substance. It's usually like 1 gram, or it might be 1 kilogram of that substance, 1 degree. How much energy it takes to raise 1 unit, 1 degree. Specific heat. And you guys who've had biology, what do we say about the specific heat of like water? It's really, really high. Now if you look at that chart, this chart up here, you can see, here's water way up here, 4,186. Compared to like, say, iron, which is 452. What does that mean about water? It's hard to change the temperature of water. Whereas it's easy to change the temperature of iron or copper or steel. Want to let somebody in? No, you're just cold, huh? But also notice that the specific heat of water in different states changes. Liquid, this is for liquid water. For steam, it's not nearly as high. It's a lot easier to heat and cool steam than it is to heat and cool liquid water. It's also different for ice. So liquid water is the hardest of the 3 to change the temperature of. We've got an equation up here that you're going to need to become familiar with. Q equals mc delta T. Has everybody seen that equation before? Most of the time in physics, if you're dealing with a capital Q, what's it stand for? Heat. Okay. Lowercase q, anybody know what that usually stands for? We hadn't gotten there yet, but we will in a couple weeks. That's a road, yeah. Kind of looks like a Q backwards, maybe. Lowercase q stands for charge, like electrical charge. And you'll see all those symbols on your formula sheet. But this is heat. And heat is equal to mass. Now here's C. Now so far we talked about C being what? The speed of light. That's not what it is here. Again, we use all these letters over and over again. I don't know why we have the system we have. But here the C stands for specific heat. And the delta T is the change in temperature. MC delta T. So essentially, why would this specific heat number be important to know? Well, it turns out it's constant. So let's say you had some piece of metal and you didn't know what the piece of metal was, and you wanted to identify what metal it is. You can actually do an experiment, and we'll look at a problem in a minute where you do this. And I think you guys just did it in chemistry, essentially, right? You allowed to take a metal and heat it up under water. No? Okay. I think you worked some problems with pieces of metal there? Because she came and asked me about a problem. No? No. Anyway, we'll see a problem where you can use these specific heats to identify what the substance is that you're dealing with, because they're constant. Remember that if it's a positive Q, that means heat is being gained. If it's a negative Q, it just means heat's being lost. We'll go ahead and look at this while we're here. This is a phase diagram. Let's put some numbers on here. Let's say that down here this was negative 10, maybe degrees Celsius right here. And let's say this is 0. Let's say right here, let's say this is 100. We're talking Celsius. Let's say this is a diagram for water. So down in here, we've got water at negative 10. What, can you get water at negative 10? Turns out you can get it below 0 a little bit if it's a mixture of what? Ice and water. You can get it a little bit below 10. A little bit below 0 if it's a mixture. But let's say, now notice we're adding heat now. So as we go left to right, we're adding heat. So when we start adding heat at negative 10, what starts to happen to the temperature? it starts to go up. And we can continue to add heat. And in this particular part of the graph, that equation will work. Let's say we know how much water we have. We know the mass. This is probably mostly going to be ice, right? So we can look up the specific heat of ice. It's on the previous slide. And how much are we trying to raise the temperature here to begin with? From -10 to 0. So we can plug that in and we can calculate how much heat it would take to raise a certain amount of ice from -10 up to 0. For right now, let's just say we have 1 kilogram of ice. We're starting with 1 kilogram of ice. So if we wanted to know how much heat it would take to go from -10 to 0, we would say Q equals 1 kilogram. Flip back to that previous slide and get that specific heat of ice. I never have that one memorized. So it's 2093. And the units look like that. Kilograms are going to cancel. And the change in temperature we're looking for is what? It's 10, positive 10. Notice the Celsius cancel as well. So to take 1 kilogram of ice from -10 up to 0, it takes 2,093 joules of heat. Now notice when we hit 0, that's sort of a magic number, right? We hit 0 as magic. What happens at 0? Yeah.
Why would it be 20,000?
Oh, I missed the 0. Yep. 20,000, sorry. Miss the 0 there. But being back to what I was saying, when we hit 0, we get to the freezing point. I mean, the freezing point, which is also what? The melting point. And if we're continuing to add heat, we're going to melt. If you have a cup of ice, and you stick a thermometer in icy water, and you start to add heat, let's say you start out at 0, you're adding heat. What happens to the temperature for a long time? It doesn't move. It stays at 0. And it stays at 0 until what happens? Until all the ice is gone. Because at that point, when that icy water starts to absorb heat, what does it use that heat to do? Melts. In that case, when you're adding heat and it's causing a change of state, sometimes the heat is called latent heat. Any idea what that word might mean? Latent? Sometimes you might have a latent infection. It means hidden. Can't see it. Can't detect it in this case. You're adding heat, but it's not causing what? A change in temperature. But it is causing what? A change of state. So let's go to another slide and we'll come back to this in a second. We need to know how to calculate this as well. And this is just Q equals M times L. And again, it's heat equals mass. And the L is the latent heat of transformation. The heat that's causing the change of state. Now it turns out that L can be two different things. If we're melting or freezing something, it's called the heat of fusion. And that has a specific value for each substance. It's a constant, just like specific heat. Water has a certain heat of fusion. Other things have, their own heat of fusion. If we're talking about turning from a liquid to a gas, or from a gas to a liquid, the L is called the latent heat of vaporization. This L is a different number than that L. They're both constants, but it depends on what change of state we're trying to do. So back on our diagram. They're at 0, we're trying to melt. So we need to know the heat of fusion for ice. So I'll come back to this slide in a minute. I'm going to slide through and find that number for us. Got it in here somewhere. There it is. Notice the heat of fusion of water is 334 joules per gram. 334 joules per gram. So let's go back here. Remember, we've got 1 kilogram of ice water. In this particular part of the graph, we're going to use the equation Q equals ml. And our M is 1 kilogram. And our heat of fusion was 334 joules per gram. Now, do we really need to use that? This is in kilograms. So 334 joules per gram would be how many joules per kilogram? We'd have to go 1,000 grams, 1 kilogram, right? So it'd be 334,000 joules per kilogram. Now that sounds like a crazy amount. But what do we know about a joule? It's not a big unit of energy. It's a pretty small unit of energy. When we multiply this through, this is telling us that it's going to take 334,000 joules of heat to do what? Change the ice that we started with over here at 0 to what over here still at 0? To liquid water. That's the heat of fusion. So far we've used this much heat to melt, and we used this much heat to do what? To get the temperature to 0. Well, in this section of the graph, now what are we trying to do? Raise the temperature, right? So what's the equation that we use when we're trying to raise the temperature? MC delta T. So in this section, Q equals MC delta Q. Again, our mass in this problem was a kilogram. Our specific heat of water we saw a second ago. Anybody remember what that was? 4186, and that's joules over kilograms times Celsius degrees. And how much are we trying to change the temperature? We're trying to go from 0 up to 100, right? So 100 degrees. So Celsius degrees cancel, kilograms cancel. We've got an amount of heat here of 418,600. And again, if we add that many joules, that's going to take our liquid water at 0 and raise it to what? What do we still have up here? Still have liquid water, but it's how hot? 100 degrees. All right, so now we're in this section of the graph. And what are we trying to do in that section? Change from liquid to gas. And whenever we're trying to change state, that's the equation that we use, ml. And again, the mass is a kilogram. And what did we say L was called in this particular change? Latent heat of vaporization. And again, that's a constant. Let's flip forward and look that up. So heat of vaporization of water, 2257 joules per gram. So we're going to take 1 kilogram and multiply it by 2257, but now that's joules per gram. So we need joules per what? Kilogram. So what do we need to do to this number? Add 3 zeros to it, right? So 2257,000. Cancel out the kilograms. So it takes this much heat to change liquid water at 100 to what? Steam at 100. And then let's say we wanted to take the steam up to, say, 120. We want to continue to heat the steam up. So let's do one more step. If we're trying to take the steam from 100 to 120, what's the equation we would use? MC delta T. Anytime you can measure a temperature change, that's the equation that you use. So 1 kilogram. Now, what are we going to put in there for that C? Steam has a different specific heat than liquid water. So let's go back and look that up. 2009, and that's joules per kilogram per Celsius degree. So the specific heat of steam, 2009. And how much are we trying to change the temperature? We said we're trying to go from 100 to 120, so 20 degrees. So then we would multiply that out, and I'm not even going to do that right now. A question that you might get on a graph like this is, the question might be, how much energy would it take to turn 1 kilogram of ice at negative 10 degrees Celsius to steam at 120 degrees Celsius? That's the way the problem would be worded. So all those calculations that we made, in the end, what are we going to have to do? Just add them all up. And we get an answer. And we'll see a problem like that in a minute. But essentially what you need to get out of this, if the temperature is changing and you want to know how much energy it takes to change it, Q equals MC delta T. If the state is changing and you want to know how much heat it takes to change the state, Q equals M times L. Remember though that there's two different L's you need to be worried about. You're going to have, on your AP Physics exam, you will have a table of constants. Now, it would make sense for you to know the specific heat of water, 4186, because you use that all the time. But no, you don't have to memorize the constants. But remember, again, there's two L's. If we're going from a solid to a liquid or from a liquid to a solid, what's that L called? Fusion, heat of fusion. If we're going from liquid to gas or gas to liquid, it's called heat of vaporization. Two different numbers, completely. All right, let's do this first. Let's find a problem here I want to look at. Let's look at problem 4. Everybody take a minute to read problem 4. I'm going to copy and paste it onto the next slide so I have some space to work it. All right, so we've got a 28.4 gram sample of aluminum. We heated it up to 39.4 degrees Celsius. We put it in a calorimeter containing 50 grams of water. So you got this hot piece of metal. 39.4 is pretty hot, right? That's pretty hot. It's what's your body temperature? 37. So it's a little hotter than body temperature. You're going to take this warm piece of metal. You're going to stick it in room temperature water. 21 degrees Celsius is about room temperature. Drop it in there. What's going to happen to the water? It's going to heat up. And what's going to happen to the metal? Cool down. And that's going to happen until they get to what? It's called thermal equilibrium, when their temperatures are equal. At that point, the heat lost by the metal should be the same as what? The heat gained by the water. So to work a problem like that, this is where we got to start. So we're going to say heat lost is equal to heat gain. Now, to calculate the amount of heat lost by the metal, we can use mc delta T for the metal. To calculate the heat gained by the water, we can use mc delta T for the water. So what's the mass of our aluminum? Yeah, let me see what my specific heat table is in, what units. I think it's in kilograms, but let's make sure. Looks like I've got everything in kilograms, so let's work in kilograms. I'm going to write down over here that aluminum specific heat is 900. And we already know that water's is 4186. All right. All right, so we're going to do everything in kilograms. So let's change 28.4 to kilograms. So it's going to be 0.0284 kilograms of aluminum times the specific heat, which was 900. Oh, we are, aren't we? Sorry, you don't know that. Imagine that's not on the board. All right. And we'll just plug in C. And what's the temperature change of the water? We're starting off at 39.4, and we're dropping down to 23. So it changes 16.4, right? Everybody with me? Right, but the metal's in the water, right? The metal's in the water. So 23 is what point? It's thermal equilibrium. It's because eventually they're to get, once we stick the metal in there, the water's going to heat up. The metal's going to cool down. And when the temperature stops changing, they're both at the same temperature, right? So that's what the 23 is. So our aluminum changes 16.4 degrees. That's my next point. When you're doing these delta T problems like this, it's going to make your life a lot easier if for the temperature difference, you just do the absolute value of the temperature difference. Subtract them, put a positive number in there for the temperature difference. Because otherwise you're going to end up getting negative specific heats, which you don't want. So I would just make this be a positive number in terms of what we're doing right now. All right, we're going to set that equal to the heat gained by the water. So the water, we've got 50 grams of it. So it's 0.050 kilograms. You know the specific heat, 4186. And the temperature change of the water is just 2, right? So we cancel out the units that we can cancel out. I'm going to go ahead and multiply. So I'm going to multiply that right side. I'm going to go 0.05 times 4186 times 2. Okay, so over here on the right, I get 418.6 joules. That's just the right. To solve for C, I need to divide that by 16.4. And I also need to divide it by 0.0284. So let's divide that out. Do I know him?
And that puts you in joules.
Yep. So my answer is telling me pretty close to what we cheated and looked up. My answer is telling me 899 joules per kilogram times Celsius degree. Let's think about this unit for a minute. What does that unit mean? Because that is the appropriate unit for specific heat. It means if you have 1 kilogram of this substance, aluminum in this case, and you add 899 joules of heat to it, what happens? Temperature goes up 1 degree. 1 degree Celsius. So if you have 1 kilogram of the substance, you add that much heat, 899 joules, the temperature goes up 1 degree Celsius. So this is what a calorimeter problem would look like. Because everybody's seen something similar to that before. No? Well, you didn't take AP chemistry, right? Everybody else in here did, right? Chris did. Okay, so Chris and Clay did. All right, we've got time to maybe work one more. Let's go ahead and try to do this one right here. Mm-hmm. Yes, but it would have to be like mercury, for example, will actually start to evaporate at room temperature. So if you had liquid mercury in this room right now and just had it laid out,
So crazy.
you could get mercury poisoning just from sitting in the room.
That's what the math hat is about. It's the hatter just put mercury on the rims of the hat to keep it nice. And they would go nuts when using it.
Yep. Okay, so let's try this one real quick.
Don't all metals evaporate? They just evaporate at such a high temperature that you wouldn't be able to.
Yes, they could, but most of them it's like a crazy high around the temperature.
Like in the sun, it does that.
Right. So here we've got a piece of zinc. We're heating up our piece of zinc. We're putting it in water, in a calorimeter. We're looking, the temperature of the water changes from 20 to 22.5. We know, in this case, we know the specific heat of zinc. We're trying to find the temperature that the zinc started out at. So, let's think for a minute. This is the idea where we talk about the heat lost by the zinc is equal to the heat gained by the water. So the heat lost by the zinc, MC delta T. Heat gained by the water, MC delta T. Now we know everything in there that we need to know except what? The initial temperature of the zinc. We know the final temperature of the zinc, right? Final temperature of the zinc is going to be 22.5. The zinc is cooling off, right? So the final temperature should be less than the initial temperature, correct? So I'm going to write this equation a little bit differently to help me figure this out. I'm going to write it this way. MC, instead of writing delta T, I'm going to say Ti minus Tf. That's not the way you usually find the change in something, right? How do you usually find the change in something? Final minus initial. Why did I write it that way? I wanted to get a positive number. The negatives is just going to throw us off. So I want to get a positive number, so I know the initial temperature's hotter because it's cooling off. And then I'm going to just set that equal to MC delta T for water. Everybody with me on that? So now let's go ahead and distribute here. So I'm going to have MC times Ti minus MC times Tf equal to MC delta T for water. Everybody good there? And now let's just plug it in and solve. So let's do kilograms. So let's go, Oh, okay, we got everything in grams, right? But our specific heat of water, well, we can change the specific heat of water. We work it in grams. So let's go 2.5 grams times the specific heat of zinc, 0.39, times Ti. Ti is what we don't know, right? I want to run out of space here. Minus 2.5 times 0.39 times TF. TF is going to be 22.5. I'm not going to have any room here. All right, and that's going to be equal to the mass of the water, 65. The specific heat of water is 4186 joules per what? Per kilogram. So we need to do what to that number to get it in grams? Divide it by 1,000, right? So instead of 4186, it'll be 4.186. And it would be grams per Celsius degree, like that. And how much is the temperature of the water changing? 2.5 degrees. We can cancel grams and Celsius degrees there. All right, I'm going to try to make some space here by go ahead and multiplying out a few things. So I'm going to multiply out the water stuff. 65 times 4.186 times 2.5. All right, so when I multiply out the water side of the equation, I get 680.225 joules. That's just the water side of the equation. That's equal to, I'm going to go ahead and do some multiplying here too. 2.5 times 0.39. That gives me 0.975. And that's going to be joules per Celsius degree. And I may not quite get through here, guys, so let me just get this set up real quick. Multiply that out. 2.5 times 0.39 times 22.5. And you guys can finish solving it from here, I think. I'll let you finish that from there.
Peter.
See you, bud.